Okay, we'll get started. As I said in the email, the focus of today's talk is on PDAs. But since I looked at the two problems and found that one of them is very similar to the homework problems they're working on, so I'm thinking, why don't we also do a context-free grammars on these problems and show you an idea how to do it, that you can carry on to the homework problems yourself. And the one I'm talking about is the first problem. Some of you asked last time, how do we do context-free grammar for complex conditions like some arithmetics, right? This is the way that I will approach to this problem. First, I and j must be integers. So you just list some examples of the integer that satisfy those constraints. 2i equals 3j's, right? What's the first set of I and j that satisfies it? I equals 3 and j equals 2, right? What's the next set? That will be j equals 4. What's the value of I? 6. Next set. 6. Sorry. 9. Do you see the patterns by now? If you don't see, we can continue. 12, 8, 10, 15. Why do I calculate so fast? Because every time I increase by 3 and j increase by 2. Can you write a context-free grammar that carries certain property? Yes? What is it? So S will generate something. 3 A's. 2 B's. Right? And empty string. Good point. Is that easy? So, yeah, the way I deal with it is just to list certain examples to figure out the patterns. And once you have the pattern, then writing the grammar is very easy. And I assume the same argument goes to the homework problem. And yeah, the focus today is not context-free grammar. So now we need to construct the PDA for it. What do we do? The normal, okay, can I erase some part? Probably the examples. I would prefer to prove the context-free grammar and its PDA side by side. So this is a normal star. We start from a start state, and we put in the dollar symbols to keep track of whether the stack is empty or not. Right? And starting from here, what do we do? Remember, 2 i's equals 3 j's. So if we talk in terms of weight, which one of A and B has a heavier weight? I, right? So yeah, first we talk about the purpose of the stack. What can we do with the stack? In DFA or NFA, we only have the states, not the stacks, right? So we kind of have certain memory over what might have happened before, and the stacks give you more expressivity by giving you the ability to count certain things and to distinguish between certain things. We'll see from this example that A has heavier weight, right? And A occurs in the front. So if we read A, we can put certain symbols into the stack to remember how many A's we've read. But that's not the purpose. The purpose is to keep track of the weight. So if we read A, we'll put in one symbol. Okay, it's difficult to write here. So what does the loop do is if it reads A, it put two ones into the stacks to keep track that there are, let's say A will have the weight 3 and B will have the weight . So the weight of 2 A's will be equal to the weight of 3 B's, right? So if we read an A, we'll put 2 ones there, remembering that the weight in the stack is 6. So if we have 2 ones there, then we must consume 3 B's to eliminate the 2 ones. Which will correspond to here. Sorry, what was it?
You have to read 3 A's, right?
No, we have to read 2 A's.
3 A's. Look at your grammar.
Oh, okay, sorry.
So go on the bottom one, right?
Yes.
It's going to go off.
Right.
So then with that, do you make it into like a triangle instead of 2 arms, or do you read an A going from the A branch to the next branch?
That's right. Okay, if we have 3 A's, then we'll have to have 2 B's. Okay, I'm running out of space.
How do you pump the last one?
Yeah, that's why that's you have to pump the dollar sign.
No, but if you only have 2 B's, then you can't pop the last one of the stack that you added. Because you pushed 3 ones on, and then you popped off 2 ones in B. You'd end up in a reject state if you were trying to pop the last one.
Okay.
Would you use 2 for A and then come up?
It's 2 for A and 3 for B. It should be the. like that. So if you read A, you put 2 1s there. And if you read a B, you pop 3 Bs out. Sorry, you pop 3 1s out. So to completely pop out the 1s, you have to, for example, you have to have at least 3 A's and 2 B's, so that it can be popped empty.
So every time you go around the A loop, you push 2 on.
You push 2 1.
And every time you go around the B loop,
You pop 3 1s.
So what ensures that you don't?
Because if you go directly here, then there's nothing to pump. You cannot read B. Right? If you come to here without reading any A, then the only way you can go is here, that pop out the dollar sign, which corresponds to the empty string.
How is this accounting for 3 A's?
So if you have A, you put in 2 1s. Then if you only have 1 A, you cannot read B. Right? Because if you have a B, then you have to pump out 3 1s. The only way you can make it the integer division is to first have 3 A's here, so that we have 6 1s, and then we have 2 B's to pop out 3. Get that? Yes, no? Make sense?
why?
Why is that? So we see the first edge that goes down for the A.
Right?
It's A comma like that.
Right.
The second one got the epsilon instead of A comma.
Oh, because for each A we want to put in 2 1s. That's because. Right.
You had to consider reading in A each time, like reading an A symbol each time. To make sure it's an A before you put like 1 on the stack.
No, because by writing an A here, we would be forced to consume another A, which is not what we want. Yes?
I think it would help everybody. I know it would help me if you went through an example with us showing the stack.
Okay. I'll remove this one, the context-free grammar. Let's say A, B, B, the most simple, the first legal string. The stack first will have a dollar sign, and when we have the first A, we will have 2 1s here, and second A we'll keep putting 2 1s, and the third A we'll put in another 2 1s. So how many 1s are there? 6. Then if we want to pump out all the 1s, how many B's do we need? Because each B pump out 3 1s. How many B's do we need to pump out the 6? That will be exactly 2 B's. Yes?
What is that last, before the except state, what is that last state for?
Oh, this one?
Yeah.
This one is just to say that we pump out the dollar sign.
You could just replace that. You don't need that. No, because you've got that empty transition.
That's true.
Don't need any input and don't do anything to the stack.
That's true. We can do a dollar sign here.
Yeah, I was just wondering if it state seemed extra.
Yeah, that will work too.
And how will you go, will you have another, instead of popping up the dollar sign?
Yeah.
Will you have another loop that goes back to the A loop so that you can keep growing the string?
No.
Yeah, you read all your A's first. Okay,
Right.
never mind.
Yeah, that will screw up the order of A and B.
Yeah.
Everybody got the idea? So the stack actually kind of remember the weighted value of each symbol. That you can use this trick to carry over whatever weight of each symbol. It's fine. Everybody got the trick? Yes? Okay. And yeah, my style will be you doing the second problem. Even though they are not quite related, but I would say it's simpler. So you do the context-free grammar for it and write the PDA for it. Yes.
I just wasn't listening. On the A loop,
Yes.
why is that, on the second, when you're looping back, why is that an empty string? Why is that an A there?
Oh, because this trick we use, this works like producer. We want to say that each A produces 2, 1.
Oh,
That's why we have epsilon.
okay.
Yeah, same here. Each B consumes 3 ones. Yeah. The context-free grammar should be easier. Well, you can,
Because both are variables.
if we do that, they will be more complex.
Here, how do we form a table like I and k can be any value?
Yes? I and k can be any value.
J can't be anybody.
J can be any value too.
It can't be. Could it be 0?
Well, it cannot be 0, that's true. And 1.
Well, I guess
It can be
if
1.
I
It can be
can
0
be
too.
0, okay.
I and, yeah. I and k are 0s and J is 0.
How do we find a pattern?
That's right.
Yeah, actually, this one does not require any pattern. Oh, there is a very simple pattern that you can see directly from the equation.
So anytime you read an A, you need to read a C, or anytime you read a B, you need to read a C. So A and B both add to the stack, and C takes away from the stack.
So J is the largest number.
Oh, I was looking, yeah, okay. Same pattern, but wrong.
Yeah. First, what's the context-free grammar for it?
Yeah. Just came up with the idea. Still working on it.
That's the right idea. The math always spit out. Right. You almost spit out the answer.
Close.
Yeah.
Say that again, you said correctly?
So A's and C's sort of add to the count, right?
Yeah.
And then B takes away from the count. So anytime you have an A, it adds to that sum. Anytime you have a C, it adds to the sum. Anytime you have a B, it kind of takes away from the sum, right? So
Except,
the two of them are adding to B the other.
except that B occurs in the middle.
Yeah. No, I think B you have to take away from the stack. And then A and C. J. Yeah, because B is represented by J. So you have to take away as many items. I did the same thing just like.
Anyone come up with the context-free grammar? Or at least a pattern in it. Should we talk about the pattern together? Or you need more, you just need a little more time to figure out? Okay guys, let me do the first step. What are the patterns? empty string A, B, B, C, A, B, B, C, A, B, 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 C, C, A, B, B, C, something like that. So the number of B must, the number of B must equals the number of A plus the number of C. What does it mean? Whenever you generate one B, you must either generate an A or a C. Now can you write the context-free grammar for that? That should be very easy now, right? Tanya, you want to try? I think the difficulties comes when you try to write the PDA for it. And empty string. Okay.
When we get a A, we have a B. When we have a C, we have a B.
Yeah, so I will write it in a more simpler way. No, that doesn't work. You're right. Everybody agree with this grammar? Right? It's exactly the idea, right? Every time you have a B, you must have an A. Every time you have a every time you have a B, you must either have an A or a C. That's it. Now what's a PDA? I think that's what everybody have. Then what do you do with B? This one will cause a problem, right? The idea that Matt described.
No,
Because so for example, you have A, B. A does not put enough ones in there to be pop out.
for every A, you put in a 1 that must be taken off by a B. And then you need to account for C's too.
Then you need to account for C, right?
Can you push C's and then pop B's in?
Well, C comes later.
Can you push 1s from C and then pop them when you, oh, you're going to B?
Yeah, the problem is when you read a B, you don't know what happens for C's.
So we can pop up the same number of ones as A has pushed, and then non-deterministically then push the number of ones which is the C we will pop.
J minus I.
Okay. Here's one idea. Like this.
I was thinking you make a epsilon transition to another state which will have that result in the same thing.
That results in the same, right? No, it does not result in the same. Because the order matters.
Dollar sign?
Yes.
I know.
Like this. And then C consume the rest of 1. Like this.
We also have an epsilon transition from stage 2 to stage 4.
Stay to
2. A to 4.
Oh.
To the second.
this one. Oh, sorry.
So in my solution, I've inserted a stage between the
Let's see what this will do. Then the epsilon transition, basically,
between those two, the first and second stage.
the loop doesn't need to be go over, right? So the C can consume the ones from A.
So you've got an excellent transition.
No, even if you don't read A, you can start with a B.
You have the excellent transition.
That's the idea.
Yeah, but the epsilon transition will go all the way to here.
And A is 0, so
You don't need to read A's anyway.
No, you don't need to read B's to consume the ones.
Yes.
Because C will consume the ones that put in by A.
Why do we need that extra transition on the bottom side?
No, we don't need.
No,
It's just the A's.
even
If
for
there's no
that.
A's, you just skip that
you already
state.
have that.
And then
Two upside.
you skip the second state, or the third state, and then
Let's see whether this solution works.
still need our dollar sign for the final.
Well, then B's can both produce one and consume one. So you don't need C. Which means it doesn't work.
No, you don't need any C's though. You could have 10 A's and then 10 B's.
No, what I'm saying is you can have 2 B's
Or you just do B, 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 right?
because B will consume the one that they put in,
Okay.
right?
Can you give some example in which this will feel?
Sure.
Should I say?
BB. B here, put in 1, and then it goes here, it consumes the 1.
So this machine can no way. No, the first B isn't going to do anything because you don't have a 1 on the
Yes.
stack.
Oh, sorry,
Yeah.
that's right.
There's a pop-up for a person.
So now you're adding a 1 and then you're adding another 1.
That's right.
That's still, so it should reject.
that's okay.
Still
That's okay, that's okay. That's not a counterexample.
Yeah.
So you first have to Yeah, so the first bit you read, you have to go here. Then you have to have C to consume the ones. Then it seems to be correct. Yeah. Those steps. Yep, it seems to be correct. Well, the one I have in mind is this. I'll skip those things. You distinguish between A and B's. Sorry, A and C's.
It just does the same thing with different symbols.
It just does the same thing with different symbol. Yeah, the 0 will remember the number of C's you need to read, and 1 consume the number of A's.
We use that format of just doing epsilon between them if it's going to be epsilon transitions.
Yeah, epsilon reading nothing.
That'll be okay on test.
No, it's not.
Not okay.
So you can always just increase your alphabet to decrease your space.
Yeah. Everybody is fine? Now it's the Chomsky normal form. Yeah, Dr. Lee said he did an example in class. Is it this example?
Yeah, I think that is it.
Okay. That's why he did not suggest this problem.
Do you want to do that one again?
But you know how to do it, right? At least. Well, actually, this problem is the one that Dr. Lee suggested. I'll simply write it down here. That's a pretty difficult problem. So remind that last time we did a problem similar to this, except like what we generated was a string that has as many A's as B's. Has at least as many. Now here is the arbitrary string whose number of A is twice as many of B's.
Doing that last one?
Yes. Basically, for each generation of B, you have to generate 2 A's. But you have to guarantee is that the string can be arbitrary. So the order is arbitrary.
So, anywhere now?
Yeah, A and B's can be anywhere. Can I erase the PDA? Yeah, basically, for each 2 B's, you have an A. And the only 3 possibilities, A is here, A is here, A is here. That's the simplest case. But how do you...
Should that be the other way around? For every 2 A's? you
Sorry,
have a B?
either A is here, or, so either this way, or this way, or this way. Right. But how do you make sure the rest of the string is rendered enough?
That's not the language, though, is it?
It's not a language. But for, I would expect for each rule there, it should cover these cases.
Wouldn't there be one more?
There's no more. So exactly twice as many. No, the other way. You're expert in this kind of questions.
Is that like the one we did last week where you just have and then you can just kind of repeat it?
You have to somehow guarantee
That there's not a sigma at the beginning, huh?
well, this one will say it always end with BA. Oh, AA is here.
But I guess the only problem is that you could have, you could start with sigma, which would be an empty string, and so you can't have that, right? Can you have an empty string here?
Empty string is covered, right? You generate 2s and each is generate an empty string.
Is that in the language?
Empty string is in the language, sure.
So you think this is?
Well, it could be correct. I don't know yet. It's not the one that had wrote, but it's very close. It could be correct. Just Jeff, let's write it down. We'll see whether it's correct or not.
You guys will shoot me down.
Yeah, last time Jeff wrote more A's than B's.
That was equal number of A's and B's.
Yeah, at least.
A is equal to B, the number of A's are equal to B.
Right. It's pretty similar. They say, how do you randomize this grammar to generate random strings? And can you explain what?
Yeah, sure. Actually, this is from my idea from the one last week, which is actually from example 2.3 in the book and example 2.3 in the slides, which is there's an equal number of A's as there are B's.
Do you still remember?
Yeah,
your solution?
Yeah, the solution, yeah.